Welcome back from that break. We've been focusing on graphs, in particular, how to plot a graph and how to sketch a graph. These are important skills, but another very important skill is interpreting graphs. Let's go and have a look at what we need to do. So when we interpret graphs, it's about recognizing what the type of relationship is. And the type of relationship we can see based on the shape of the graph. So the shape of the graph gives us a very good indication of what's happening between the variables. And I want to remind you about the different types of relationship that are related to shape. So where do we begin? What's the most common graph that we come across in either physics or chemistry? Well, it's that one that has a straight line to it, that passes through the origin. Have a look here. So this graph, which is one that we've referred to before, a distance and time graph, you can see that even though some of the points aren't exactly on the line of best fit, it gives you a trend that is a straight line. It's not, can't be confused with some sort of funny curve. It's a straight line. And the straight line has a constant gradient. This means that this equation, the equation of this line, is in the form of y equals mx plus c. And that's the maths part of this lesson. But notice something about the y-intercept or the vertical intercept. It's equal to 0. So when c is equal to 0, we've got y equals mx. And guys, if we've got y equals mx, that means that whatever we do to x, we're multiplying x by a constant, and that will give you y. So the y divided by x is going to be a constant. That tells us that this relationship between these two variables is directly proportional. So that's an important word to remember, and it's an important feature to take note of, directly proportional. What it means is that if you increase the independent variable by a certain factor, then the dependent variable is going to increase by the same factor. As the one goes up, the other goes up, but by the same proportion. So if you double the one, you double the other. And that's what you can tell by looking at a graph with a straight line, but it must pass through the origin. Look at this one. So this graph, it's a straight line, but notice something about it. It doesn't pass through the origin. This is not directly proportional. It's not directly proportional. The gradient is constant, is equal to a number, it's a constant, but it doesn't mean that the relationship, if you double the one, you're not going to double the other, because in this type of graph, the equation of the graph is related to that full equation of y equals mx plus c, and the c factor stops it being totally proportional. So that's very important for you to understand, that when we've got these sort of relationships, the equations are going to look a little different. Whereas when it's directly proportional, like in the previous graph, what you're going to find is that in this graph, we can put it into an equation where we're going to say something like this, that velocity is equal to the change in distance over the change in time. And so we can manipulate that into an equation that actually makes sense and we can use to do some calculations. The two are related, and so I hope you've got that very clearly in terms of where we're going. So those ones had straight lines, but what happens when you get one that is a curve like this? So very clearly this is a curve, and it looks to me a bit like a parabola, or part of a parabola. Parabola. Sorry, my spelling's not very good, but we've got it. So I need you to understand something now, that if you see something that is like a parabola, even a quarter of a bit of a parabola, half a parabola, look and see it's going through the origin, and if we reflected this about that vertical axis, it would make a nice up-shaped, smiley-faced parabola. It would go right round like this. Now, it's a graph of kinetic energy against velocity. Now, you should know that kinetic energy is equal to half the mass times the velocity squared. And if you look at that, you'll see that it's really in the form of y equals ax squared, where this half m is equivalent to the a. So if we want to check, is it a parabola or is it maybe something similar to a parabola, what do? We've got to do another type of plot. Instead of plotting the y value, the kinetic energy against velocity, we're going to say, let's plot the velocity squared against the kinetic energy. Now, if we plot then this is going to be a constant. What do you predict if you do that? Well, it would be a straight line. And so we can see the relationship from the shape and from the axis. So looking at the axis, you'll see this is velocity squared, and this is EK. So we've got EK is directly proportional to velocity squared. Why would I say directly proportional? Well, look at it. Look at that pink line. It's a lovely pink line. It's going through the origin, and it is a straight line that's going through most of the points. So we can say kinetic energy is directly proportional to velocity squared because of the shape of the graph. And so what would the gradient be here? This gradient is going to be equal to half the mass of the object. And how did we get that? Well, we saw originally the equation is EK is equal to half m for mass, v squared. So if we look at EK over over v squared, then you're left with half m on that side. So the gradient is a very particular thing, and we can write this in the form of y equals mx. And that's exactly what I'm doing here. So in the form of y equals mx, what I'm saying is that's my y, the EK is the y, the x is the v squared, and this part here is the m, which is the gradient. And so we can say, as I've written it over here, from this sort of graph, EK is directly proportional to the v squared. Now, what other sort of relationship have we got? We've got directly proportional, a squared relationship, and the last one, which is also very important, is an inverse proportionality. And so we're not going to make it too difficult, but let's have a look at an example just to show where we're at here. So the points here seem to make a bit of a curve, and I'm going to plot them like that and draw in the line that's kind of the line of best fit. And the question is, so is this a parabola, or what sort of graph is it? It's got a curve to it, but we're not really sure. And so there's a mathematical trick that we can use, just one of the many tricks that physicists and chemists use to try and establish the relationship. So like we did in the other one, we plotted EK against V squared. Here we're not going to just take the graph of pressure against volume, but because we can see as the one is increasing, the volume is increasing, the other is decreasing. It looks like as the one goes up, the other one goes down. Let's rather take the reciprocal of the one. That means 1 over. So what I'm going to do is I'm going to take volume and I'm going to change it to 1 over volume. And if I do that, look what I've got. That minus 1 there represents the 1 over. That minus 3 represents that it's 1 over. And so here we've got the graph showing the pressure of a fixed mass of gas and the reciprocal of volume. It means 1 over volume. And so what we're saying in this graph is that pressure is directly proportional to 1 over volume. Notice it goes through the origin, and the gradient here is a constant. What do you think that gradient could represent or contain? Well, it would contain a factor that relates to the mass of the gas, and I also know that it could be related to the temperature of the gas at that particular point that we're measuring it. So the graphs tell us many things. The shapes and the relationships are determined, and we can interpret them. It's important to look at them and to see. But guys, these aren't the only things to look at. We do need to keep in mind this relationship between an equation, the graph, the shape, and the relationship. And I think that makes a lot of sense for us to make sure that we've covered the most important skills when it comes to interpreting and linking our interpreting to the relationships, because the relationships that we've looked at, directly proportional, where the graph looks something like that, where this is going to be a value like distance, this one is time, this one, the squared relationship, where we had kinetic energy against V, and that was what the graph looked like, and then we changed it. We said it's the kinetic energy, which is EK, plotted against V squared, and we found that it was a straight line. And finally, the inverse relationship, we had pressure against 1 over volume, and that was a straight line that passed through the origin. So please make sure that you understand these relationships. By looking at the shape, you're going to say, so what's happening as I change the one variable? What's happening to the other variable? I know that's been a lot to think about, and so you know what? I think you deserve a good break. So take a stretch, take a deep breath, have a drink of water, and we'll be back straight after this.